Competency number 4, module 1.2.4. So we are going to see tubular reactors. Gas phase reactions are carried out primarily in tubular reactors, where the flow is generally turbulent. By assuming that there is no dispersion and there are no radial gradients either in temperature, velocity, or concentration, we can model the flow in the reactor as a flow. So, the differential form of the PFR design equation FA0 times dx divided by dV equal to minus RA must be used when there is a pressure drop in the reactor or heat exchange between the PFR and the surroundings. In the absence of pressure drop or heat exchange, the integral form of the flow design equation is used. And so here we have this integral form in which the volume is equal FA0 times dx divided by minus RA, and that is equal to FA0, the integral of dx divided by minus RA, with the limit from 0 to x. As example, let's consider the reaction A goes to product, for which the rate law is equal minus RA equal K Ca squared. This means that it's a second order reaction. We shall first consider the reaction to take place as a liquid phase reaction and then to take place as a gas phase reaction. For a liquid phase reaction, we know that the volumetric flow rate B is equal to the initial volumetric flow rate B0. If we combine the PFR mole balance and the rate law, we will have that dx in dV equal to K Ca squared divided by FA0. And if the reaction is carried out in a liquid phase, the concentration of A according to the stoichiometry in liquid phase is going to be Ca equal to Ca0 times 1 minus x. And for the isothermal operation, we can bring K outside of the integral because it's a constant. So we will have that the volume is going to be FA0 divided by K Ca0 squared times the integral of dx divided by 1 minus x elevated to the second power. So this is going to be equal to B0 divided by K Ca0 times x divided by 1 minus x, because the integral of dx divided by 1 minus x to the square is 1 minus x to the minus 1. The limit of the integral from 0 to x. This equation gives the reactor volume to achieve a conversion x. If we divide it by B0, the volumetric flow rate, so we will obtain tau, because tau is the volume divided by the volumetric flow rate. We will have that x, the conversion, is going to be tau K Ca0 divided by 1 plus tau K Ca0, but tau K Ca0 is the Damkholer number for a second order, so x is going to be dA2 divided by 1 plus dA2. Now, in the gas phase, for constant temperature T equal T0 and for constant pressure P equal P0, the gas phase reaction, then the concentration is expressed as a function of conversion, because the stoichiometry in the gas phase, Ca equal to Fa divided by the volumetric flow rate, but the volumetric flow rate is B0 times 1 plus epsilon x, so the concentration of A is going to be Fa0 times 1 minus x divided by B0 times 1 plus epsilon x, but Fa0 divided by B0 is Ca0, so we will have that Ca0 times 1 minus x divided by 1 plus epsilon x. And if we combine the mole balance, rate law, and stoichiometry for this PFR, we will come that the volume of the reactor is going to be Fa0 times the integral of 1 plus epsilon x squared divided by kCa0 squared times 1 minus x squared with the limit of 0 to x. The entering concentration Ca0 can be taken outside the integral since it's not a function of conversion, and because the reaction is at temperature constants, K is going to be out of the integral too. So we will have that the volume is going to be Fa0 times kCa0 squared, the integral of 1 plus epsilon x to the second power divided by 1 minus x to the second power from the limit from 0 to x. And from the integral equation of appendix A1, we will have that for that integral, the appendix of our book tells us that that integral is equal to 2 times 1 plus epsilon natural log of 1 minus x plus epsilon squared times x plus 1 plus epsilon to the square times x divided by 1 minus x, and all that multiplied by B0 divided by kCa0 is the volume of the reactor. If we make a plot of the volume against x, we will have this plot. And here we see that for a reactor of volume, let's say any value of the volume, let's say 8, we will see that for a reaction in which A goes to 3B, for this volume, we will have a conversion lower than if the reaction goes A to 2B, or if it goes from A to B, or if it goes from A to B divided by 2. So if the reaction goes from more reactant than product, then the conversion is bigger. And here we have, let's consider 3 types of reaction. One in which epsilon equals 0, delta equals 0. One in which epsilon is less than 0, delta is less than 0. And one in which epsilon is higher than 0, delta higher than 0. Then, when there is no change in the number of moles, by example, A goes to be 1 to 1, delta is equal 0, and epsilon is equal 0, then the fluid moves throughout the reactor at a constant volumetric flow rate B equals V0 as the conversion increases. But when there is a decrease in the number of moles, delta is less than 0, epsilon is less than 0, in this gas phase, that means that 2A goes to B, there is a compression. The volumetric gas flow rate decreases as the conversion increases. For example, B equals V0 times 1 minus 0.5x. Consequently, the gas molecules will spend longer in the reactor than they would if the flow rate were constant, B equals V0, and as a result, this longer residence time will result in a higher conversion than if the flow were constant at V0. And on the other hand, if there is an increase in the total number of moles, delta will be more than 0, higher than 0, epsilon will be higher than 0. In this case, in the gas phase, A goes to 2B, then the volumetric flow rate will increase as the conversion increases. For example, B equals V0 times 1 plus X, and the molecules will spend less time in the reaction, and they will if the volume flow rate were constant, and as a result of this smaller residence time in the reactor, the conversion will be less than would be if the volumetric flow rate were constant.